every edge is visited only once, right?
Yes,
And you return to the vertex that you started at for a circuit.
yes, that is exactly right. So an Eulerian circuit is a circuit that traverses every edge of the graph exactly once. It begins and ends at the same vertex. That's exactly what an Eulerian circuit is. What is an Eulerian path? Okay, again, we're traversing a graph. We want to start at some vertex, only this time we want to end at another vertex, and we still want to cover every edge of the graph. Okay, that's exactly right. Okay. Now, so what are the criteria for the existence of Eulerian traversals? Let's start with the circuit. So last time, the whole conversation was about determining what kind of graph should our graph be. Our undirected multigraphs are what we're speaking about. What characteristics should that graph possess in order for there to exist an Eulerian circuit in that graph? Okay, so what were the criteria?
The degree of the vertices in that graph had to be even, unless we only had two that that could be in an odd degree.
Yes. So if every vertex in the graph has an even degree, then there is an Eulerian circuit in the graph. And that's an if and only if statement. Okay, these are necessary and sufficient conditions. So so what do I mean by necessary and sufficient conditions? What is it that I'm claiming here? Anyone help me out? So I'm claiming that it is so having every vertex of an even degree is both necessary and sufficient for the existence of an Eulerian circuit. What does that mean? What does necessity mean? What is the statement, the logical statement that you can extract from the last sentence that I've said that tells me that this condition is necessary for the existence of a circuit? And what does it mean to say that those conditions are sufficient for the existence of the circuit?
If we have that, then we can talk about
yes.
Eulerian. If we don't have that, then we can claim that a graph is a
that is exactly right. That is exactly right. And that we'll talk more about this later today when we'll talk about Hamiltonian traversals of a graph. So if every vertex of the graph is we're speaking of undirected multigraphs, undirected connected multigraphs. If every vertex of the graph has an even degree, then there is an Eulerian circuit. And if a graph has an Eulerian circuit, then every vertex of that graph must have an even degree. There is no other way. Now that's the criteria for the existence of Eulerian circuits. Those are necessary and sufficient conditions. Now for the existence of an Eulerian path, that is the one that begins and ends at different vertices, what are the necessary and sufficient conditions? You must have exactly two vertices of an odd degree, and every other vertex must be of an even degree. Those are the conditions. Okay, so now let's talk about Hamiltonian traversals of a graph. A Hamiltonian traversal of a graph. Okay, so again, reminder: this is unlike an Eulerian traversal of a graph, a Hamiltonian traversal covers every vertex exactly once. So here again, in your handout, there's a brief review of the terms again. So by a path, so now you will notice that I have changed the handout that I had before, where I used trails and all this other terminology that is quite common. I have changed it to Rose's terminology so that there's no confusion in anybody's mind. I want to stick with the book as close as possible. So a path will be, for us, what Rosen calls a path. A path is simply a sequence of edges like this. So these are the edges. And notice what has to be true for a path is that for two consecutive vertices, for two consecutive edges, it has to be true that this edge here ends exactly at a vertex at which the next edge in the sequence starts. Okay, that's true for every pair here. The last vertex may end at a vertex that is the same as the first vertex. If that happens, then we're speaking about a closed traversal. Okay, well, Rosen calls that a circuit. If this first vertex and the last vertex happen to be the same. Notice that these vertices here, along these edges to which those edges are connected, need not be distinct. Okay, so a simple path, so what's a simple path according to Rosen? You read these definitions. So according to Rosen, a simple path is the path that does not repeat an edge, right? The path that does not repeat an edge is called a simple path. So for example, is this path simple? Okay, so let's trace this out first of all. This is a typical path. Why? Because every edge, these two edges, every pair of edges, okay, share a vertex. Okay, so let's trace it. Okay, so 2, 3, 5, 4, 3, 6, 1. That was a path. It started at this vertex, ended at that vertex. Notice that I've covered I didn't cover every edge, okay? But I didn't traverse an edge more than once, any edge. So it is a simple path because I didn't trace any edge more than once. It is a simple path, according to Rosen. Now, I didn't cover every edge, so it's not an Eulerian traversal. I have an edge that hasn't been covered here. I did cover every vertex, right, of the graph. I did pass through every vertex, but I also passed through some vertex more than once. In particular, this vertex 3 here was passed through more than once. Now, today we'll be talking about those kinds of traversals where we do not pass through a vertex more than once, okay? And we cover every vertex of the graph. Such traversals, in a minute, we'll call those Hamiltonian. I'll repeat what I've just said in a minute. But for more examples, here's another example of a simple path. 2, 3, 6, 1. That is a path. I mean, it doesn't cover every vertex of the graph, doesn't cover every edge of the graph, but it's some path inside the graph. Okay. What is a circuit? It has to start and end at the same vertex. Okay, so 2, 5, 3, 4, 5, and then 3 again. So notice now I'm traversing this edge the second time, and then 2. Okay, that was some kind of a traversal of the graph in which I traversed a given edge, in particular the one from 5 to 3, that edge twice. So that's some traversal, but it's a circuit because it started at 2 and it ended at 2 here. So it is a circuit. Now a cycle, and Rosen doesn't distinguish between a cycle and a circuit, but sometimes you will see that a cycle is the one that, again, it's a closed path. It starts and ends at the same vertex, just here at 2, but it doesn't pass through, okay, so all the vertices along that circuit are all distinct. That's called a cycle. Okay, so for example, 2, 5, 3, 2, that's a cycle. And you can see other cycles. Here's a cycle of length 4, for example. Okay, 1, 2, 3, 6, 1. That was a cycle of length 4, and so on. So this is just a review of terms, and we'll stick with this terminology. This is exactly Rosen's terminology here. So I've changed the previous handout so that it's more consistent now with Rosen's handout. But the examples, we'll go through the examples from this handout now. Here's a definition of the kinds of traversals that we're interested in today. Okay, sounds very similar to Eulerian traversals, but it's very, very different. In fact, despite the similarity in the formulation of these two problems, one is easily solved, and for one of them, necessary and sufficient conditions for the existence of those kinds of traversals, and Eulerian traversals, exist, and for the other, there aren't any known, at least so far. So here's a Hamiltonian path. It's a simple path in which you pass through every vertex of the graph exactly once. Okay. So notice that you're not repeating edges in this traversal, right? You are not repeating vertices either. So if you're not repeating vertices, you're not repeating edges either, right? So does that make sense? Okay. Because if you repeated edges, then you would pass through the same vertex more than once, and we don't want that. So we're passing through every vertex exactly once. Okay. So now a simple circuit that passes through every vertex of the graph exactly once. Now we want a circuit. We want to cover every single vertex of the graph. We do not want to pass through any vertex more than once, and we want to start and end at the same vertex. We'll have a cycle. We'll call that cycle a Hamiltonian cycle. Examples to make sure that this is clear. So here are some circuits in this graph. So A, B, E, D. I'm looking at the first one, C, B, and F and A. So what is that? That is a traversal of the graph. Okay, it's just a circuit. Okay, I did cover every vertex of this graph, but I passed through some vertices more than once. In particular, it passed through this B more than once. So it's nowhere near being Hamiltonian, this traversal. This is what I just traced out, this first one. It's not Hamiltonian, but it's a circuit. It started at A and ended at A. Same thing goes with this one. I'm not going to trace it out. So let's look at cycles. Here's a cycle, A, D, E, B, and A. So that was a cycle. This is a cycle of length 4. Okay, I started at some vertex A and ended at the same vertex. I didn't go through a vertex more than once, but I didn't cover some vertices. So this is not a Hamiltonian cycle. It is a cycle, but it's not Hamiltonian because some vertices were missed. Okay, so we'll be interested in Hamiltonian cycles. So same thing goes, well, not the same thing. Now let's look at this cycle. A, B, C, D, E, F, A. Now that's a Hamiltonian cycle, right? So just reverse the whole thing. Now notice that this is not the only Hamiltonian cycle in this graph. This graph has other Hamiltonian cycles. How about this A, D, C, F, E, B, A? Okay. Notice that now I've covered every vertex exactly once of the graph. I didn't miss any vertex. Of course, there were some edges that I didn't traverse, but that's fine. I want to hit every vertex. Unlike, so this is very different from Eulerian traversals. I started at some vertex, ended at the same vertex. I've covered every vertex, but I didn't go through any vertex more than once. So I went through every vertex exactly once. That's a Hamiltonian traversal of the graph. If you can find such a circuit in a graph, then the graph is called Hamiltonian. So you call it Hamilton graph or Hamiltonian graph, Hamilton cycle, Hamiltonian cycle, any way you'd like to call it. It's normally clear from the context. So whether you call it Hamiltonian or Hamilton graph doesn't really matter. So I guess we have Hamiltonian. Let's stick with that. I don't know what the book called. I think call it Hamilton. It doesn't matter. Okay. So let's see what graphs are Hamiltonian. Okay. So so let's start here. Okay. So first of all, is it clear what the definition is? Right, of a Hamiltonian cycle. Okay, so again, for a graph to be Hamiltonian, we need a cycle. Now, can I ask you this before we even get to examples? Is the following claim true? If a graph has a Hamiltonian cycle, then it has a Hamiltonian path. So what is a Hamiltonian path? What is a Hamiltonian path? Not a cycle.
It's just when you go through all the vertices, but none are repeated. But you don't have to start and end with the same.
Yes. Yes. So a path, the only difference between a cycle and a path is that the path starts, the Hamiltonian path. They both cover every vertex of the graph exactly once. Both the cycle and the path, the Hamiltonian path. They both cover every vertex of the graph exactly once. But the path, Hamiltonian path, begins and ends at distinct vertices. And the Hamiltonian cycle begins and ends at the same vertex. Here's the claim. If some H graph, let's call it G actually. If G has a Hamiltonian cycle, then G has Hamiltonian path. Is this true? And help me write down the converse. So is it true? Which one is true? If G has Hamiltonian path, then it has a cycle. Okay, so help me out.
I think the first one is true.
Okay, so first one is true. Why is that?
Like there are more restrictions on it. So like
okay.
if you can always get back to where you started, you could go just one less.
Yeah, exactly. So if you have a Hamiltonian cycle, so here's your argument, and let me try to repeat it, and you tell me if that's what you meant. So there is some cycle here in this graph. I don't know, it goes like maybe it winds around and gets back here, this cycle. So if you, okay, so you can, around this cycle, you can start and end at any one of these vertices, right? So if you have a cycle, if you just remove one of those vertices, then the rest of this traversal, the rest of this path, still covers every vertex in the graph right? But it doesn't start and end at the same vertex. So you started and ended at different vertices, and you've traversed every vertex of the graph, right? Because this cycle initially traversed passed through every vertex of the graph. However, is the converse true?
No,
Okay, so why?
Because- we don't know if the last vertex is can be connected with the one that the path started from.
Okay, so let's give a counterexample. It's much simpler. So here's
It's not necessary that it connects.
yeah. So here's some graph on 3 vertices. Is there a Hamiltonian Hamiltonian path here? Yes. So and V1, V2, V3 would be a Hamiltonian path. It passes through every vertex and it hits every vertex exactly once. But there is no cycle here. If you start at V1 to end back at V1, you must hit once you get to V3, which you must reach, and there is only one way to reach V3. Once you get to V3, there is no way of getting back to V1 without passing the vertex V2 to which you've already been. So there is no Hamiltonian cycle here. Okay, but there is a Hamiltonian path. So quick observation. If there is a Hamiltonian, if a graph is Hamiltonian, then it has a Hamiltonian path. But it's possible that a graph has a Hamiltonian path, but is not Hamiltonian. Okay, again, by definition, the graph being Hamiltonian means there is a cycle, a Hamiltonian cycle. Starts, ends at the same vertex, covers every vertex exactly once. Is this graph Hamiltonian? Real quick.
Yes.
Yes, why is that? Well, you can find a Hamiltonian cycle, right? So this is one. That's a Hamilton. Well, first of all, that's a Hamiltonian path. Is there a cycle?
Yes.
Yeah, there is a cycle. There's a Hamiltonian cycle like that. Okay, and so this graph has both. Notice that the argument that we gave here. Okay, so here you can have a Hamiltonian path here that doesn't start and end on neighboring vertices. So this argument that we gave here was just for illustration. When we claimed that if you have a cycle, then we also have a Hamiltonian path. Here I can have a path that starts at B and ends at E here, and B and E themselves are not connected. Okay, so you can have a path like this. Okay, fine. So this graph has both a Hamiltonian, it's a Hamiltonian graph, and it also, well, it's a Hamiltonian graph. So it has both the cycle and the path. So how about this one?
It's only a Hamiltonian path.
Okay, so there is a Hamiltonian path, like this Zorro here, for example. How can you argue there is no, okay, granted, this is a small example, but, and you can check every possible path, and there is no Hamiltonian, every possible cycle, and there is no Hamiltonian cycle. That's easy to see on this graph. Okay, so it's a big.
Doesn't it have to have like an even number of vertices that have odd degree, or no?
No, it doesn't. Maybe we'll see examples later where okay. Here's what.
Is it not a cycle if there's a, what's it called, a pendant?
Yeah, so this pendant vertex here, this guy of degree 1, gets in the way. Why? Because if there is to be a cycle, a Hamiltonian, suppose there is a Hamiltonian cycle in this graph, right? Let's give a general argument, although we don't really need to be that general for this particular example. We can just see it more immediately, perhaps. But let's argue a bit more generally so that the argument applies to larger graphs, which we can't immediately trace by hand. Suppose there were a Hamiltonian cycle in this graph, right? Then, well, if it's a Hamiltonian cycle, then A is a vertex that's passed through. But A has only one edge attached to it. This means that this edge here, because I'm passing through A, has to be passed through twice. Meaning that this B, for example, is passed through twice. So this edge, there's no way of avoiding traversing this edge more than once. Right? Does that make sense? So start here, go here, you have to return to B, and this B will be passed through more than once. There's no way to do it. Same thing happens here. So notice that so what we've tried to argue here is that if the graph has a pendant vertex, as a vertex of degree 1, there is no way for that graph to be Hamiltonian. Does that make sense? There is no Hamiltonian cycle there. It's also true that, well, what if a graph has a vertex of degree 0? That means it's a disconnected graph, right? So it has an isolated vertex. So it's a graph that looks something like maybe like this. Okay, so a graph like this. on 4 vertices where one vertex is isolated? Well, of course, if it's a disconnected graph, then it cannot possibly be Hamiltonian. Why? Because you have to pass every vertex and you have an isolated vertex. There's no way of reaching it. And if you started that vertex, there's no way out of that vertex to get to other vertices.
Can we call that graph an Eulerian graph, since if we're passing every single edge?
Yeah, you can, yes, you can, right? You can, this would qualify as an Eulerian, according to our definition, it would qualify. Because you will traverse every edge once and some vertex is not being traversed. But in the context of Eulerian graphs, we have in mind connected graphs. So we're really speaking about connected graphs here. With respect to these connected multigraphs, okay, so multiple edges are allowed. Now, in terms of coming back to the Hamiltonian graphs here, for example, so notice that we have determined a necessary condition for a graph to be Hamiltonian. Again, what's a necessary condition? Here's a condition, okay? If a graph is Hamiltonian, some characteristic of the graph must necessarily hold. So if a graph is Hamiltonian, then there is no way it has a vertex of degree 1 or less. Okay, so in a Hamiltonian graph, every vertex has a degree smaller than 2. No vertex in a Hamiltonian graph, no vertex can have a degree smaller than 2. So every vertex has degree 2 or larger if a graph is Hamiltonian. And notice that doesn't mean the converse is clearly not true. Okay, you can have a graph whose every vertex has degree 2 or more, but the graph still may not be Hamiltonian. So it's important to keep in mind the necessary and sufficient conditions. So this theme will recur throughout our discussion today. Okay, now back to these examples here. So let's look at this graph. Is this graph Hamiltonian? First of all, we already know it's not Hamiltonian because it has a pendant vertex. And any graph with a pendant vertex cannot possibly be Hamiltonian. So this is not a Hamiltonian graph. There is no Hamiltonian cycle in it. But is there a Hamiltonian path in this graph? So here's a graph. I don't know, maybe 4 vertices, so let's do it like that. Well, this is C4. Any cycle graph is clearly Hamiltonian. C4 is. If you attach a vertex, a pendant vertex here to this graph, all of a sudden it's not Hamiltonian. I've just added a vertex and made the graph not Hamiltonian. Right? So by the way, can I ask you this? Suppose you have a graph and you add to it edges. Is there any way to make it non-Hamiltonian? So I'm not adding any new vertices. So it's unlike, the situation is unlike what I've drawn here. I'll get back to this in a minute. But suppose you have a graph like, so this is kind of getting away from this example. Okay, so let's return to this example. So we're still working on this example. I just want to deviate slightly for 1 second. Let me erase this here. There are a couple of claims, meanwhile, while we're at it, that I want to make. First of all, nobody argues that any CN graph, okay, CN, what's a CN? Cycle graph on n vertices. So this one has, I think, C7 I drew, if I'm not mistaken, this C7, right? This is a Hamiltonian graph, right? Any C graph is Hamiltonian. It's just obviously Hamiltonian. Start at vertex and just go around. That's what makes this graph a cycle graph. It's a Hamiltonian graph. Will this graph all of a sudden, out of the blue, become a non-Hamiltonian graph if I add edges to it? So now notice I'm not adding vertices like I did here. I'm adding edges to it. Like here, maybe, I don't know, maybe I added this edge, maybe I added that edge, but I keep adding those edges.
I don't think it'll affect it because we already said if there's a cycle, then it's Hamiltonian.
Yes, exactly for that reason. So we're not adding any vertices. Hamiltonian cycles traverse the graph in such a way that they hit every vertex exactly once. If we already have such a traversal of the graph along these edges, then just having extra edges around doesn't hurt the situation because we already have a Hamiltonian traversal of the graph, right? Is everybody on the same page here? So this means, now let me ask you this real quick. So what is Kn? Doesn't Kn have all its pairs of vertices connected? And therefore, the Cn is a subgraph in it. Cn is a subgraph of K of n. So here's an example of K5, for example. Okay, so here's K5. This is C5 I just drew. And then connecting every other pair. So this is now C5. So this, I'm sorry, K5. This is K5. And this piece here was C5. So the red piece is C5. Okay. So if I add edges to C5 to augment the graph in such a way that I have every possible edge so that I get to K5, that is, make a complete graph on those vertices, then, you know, isn't K5 going to be Hamiltonian? Because all I've done is just added the vertices and I already have a Hamiltonian traversal. So do people see that every complete graph on n vertices then has to be Hamiltonian? There is no other way. And this is just one way to argue that that's the case. Another way, I think, I've looked at the book, the way the book argues is also a way to argue it, which is, well, in Kn, every vertex is connected to every other. So yes, there is a Hamiltonian cycle, and here it is, the book says. Start at any vertex. It's connected to every other, so pick any vertex that you want to go to. You have a way to get to another vertex. Then it says pick any other vertex that you haven't yet been to and go there. You can always do this because you have a complete graph. There are edges between every vertices. So use up that edge, get to the next vertex. And so no matter in which vertex you are, you have a way of getting to any other vertex. So here's a traversal that traverses the graph in a Hamiltonian way. So, but anyway, you'd like to argue, we have two classes of graphs now. We've identified, while we're thinking about this problem, it just came along, this observation, somewhat in an unrelated way, actually, that okay, we've identified two classes of graphs that are Hamiltonian. The cycle graphs, which are obviously Hamiltonian, like CNs, like this, and KNs. Those are Hamiltonian graphs. A good exercise would be to figure out what's KMN. What was our notation for KMN? It was a complete bipartite graph, right? On m plus n vertices. Remember, people? Do people remember this?
Yes.
Okay, so this is KMN. Now the question is, does this is kind of a trick question I've seen instructors just throw at people on all sorts of quizzes, and I don't like to play any tricks on people. So let's just talk about this a little bit. And this would be a good exercise if you see something like this. In case I don't know if it will show up, but the question is, when does KMN have a when is it Hamiltonian? When can you find a Hamiltonian cycle in it? So notice that you have every possible edge from one side. So this is our bipartite graph. So these are partitions, the partite sets, V1 and V2. And you have connections in between those sets, every possible connection. So first of all, notice that, okay, you should think about this, but let's take this example here. If I have the same number of vertices in the two sets, and again, I have all possible connections that I can think of. So I have 3 times 3 connections here, right? 9 connections. Is there a Hamiltonian path? Yes, because I can start it at any vertex, pick any vertex. And you can start traversing it like that until you get to this vertex. And then, of course, I have an edge there too, in between the last one and the first one. Okay, the point is that you start in one of those, in one set, V1, this is our partition, V1 and V2. You start in V1, and once you've covered every vertex, you end up in the other set, in V2. And then you have a connection back to where you started. So if you have an equal number of vertices in KMN, so when M equals N, and we're assuming they're greater than 2, right? So you just don't want to have a graph like this. So then, as we've just shown, KMN is Hamiltonian. So bipartite graph with an equal number of m and n, with the equal number of vertices in the partite sets, is a Hamiltonian graph. Now, can I ask you what happens if m and n differ?
It doesn't seem like it changes anything.
It
Really?
doesn't seem so. Okay, then let's explore.
We have.
I
we
was
have
going to
a
assign that, but let's explore it now then. Sorry,
we
one.
have a we have a path, but we don't have a Hamiltonian
Yeah,
graph.
okay, so let's take a look. So again, recall the definition of Hamiltonian. Hamiltonian means there must be a cycle. Okay, so here we have this guy. So let's think about this. I want to leave something as an exercise, but so suppose you start here. You can still go through every vertex. Now, when you end up here, you've covered the same number. So now notice that I could have picked a different vertex, but I started from a vertex in the set that's smaller of the two. So m and n now, m and n are distant from one another. So you started from a smaller one. Then if you've covered, you've traversed the graph in such a way that you've exhausted every vertex in the smaller partition. So in this case, in the one that has 3 vertices, you've covered also 3 vertices in the other, in the bigger one, in the bigger partition. This leaves this vertex out. Now there is no way to reach this vertex because there is no connection in this partition, in this set. There are no edges in between the vertices. So there's no way to reach it. Well, then you say maybe there is another way, maybe there's back to the other set and come back to this somehow. That still doesn't exist because all of the vertices here in the smaller set have already been passed through, and I cannot pass through the same vertex more than once. Okay. Okay, then you say, well, you've started at this vertex, that doesn't prove anything, and I would agree that this doesn't prove anything. I could have started at a vertex from a larger set. Well, then you have to see what's going on there. So maybe you'll end up, you started in a larger set, you end up, when you've hit every vertex in the smaller, you end up at some vertex in the larger set. And now because those two are not connected, there's no way to return back to the original vertex again, right? So a bipartite graph, and this is like very loose, you can turn this into a proof, but I think people can see it. So we don't want to get, there's no need to get more pedantic about this. The point is that the hunch that you have now, that KMN is Hamiltonian if and only if M and N are the same number. If this holds, if M equals N, then you'd be correct. So this complete bipartite graph is Hamiltonian only when the number of vertices into 2 sets are equal. And it's non-Hamiltonian otherwise. Okay, so that was kind of a lyrical digression, let's call it, from the main theme. What's happening with this graph? Why do I not have a Hamiltonian cycle there? Okay, well, I think it's clear why we don't have a Hamiltonian cycle. Because we have pendant vertices, as we discussed. But why is there a path? Is there a Hamiltonian path there?
No.
Okay, so why is that?
Is it because it's more than 2 vertices that are degree 1? It's an odd number, but more than 2.
No. It's just the fact that it's more than 2. It could be 4 of them. So this
okay.
So, but you're correct. That is correct. But the thing is, see, if I took this graph here, let me erase that. So you see this C4 with an attached edge here on the right-hand side here of the screen. This graph does this graph has a Hamiltonian path? Right? Okay, so does it have it? Is there a Hamiltonian path here?
No.
Okay. No. Well, you won't find it if you start at any of the vertices of the C4 piece of it, in the green piece. But you can start here, and you can walk down. Okay, so this one doesn't have it. This one doesn't have it. What am I talking about? I wanted to show you this.
If we connect.
Yeah. So here's what I want. So can you move the edge here so that there is a Hamiltonian path, but not a cycle? Can't have a cycle. This one. So what I did is I moved this edge from here to here. And now all of a sudden there is a Hamiltonian path. There is still not a cycle. We can't have a cycle if you have a pendant vertex. But now you have a Hamiltonian path because you can start at this vertex and traverse it like that and end up at a different vertex. So if you have two pendant vertices, there is a chance for there to be a Hamiltonian path if it's configured like this. Because, but you would have to start at one of those odd, like pendant vertices and end at another pendant vertices, right? But there is no guarantee. Unlike some, we had the Eulerian traversals, we could see some guarantees. It was a different kind of traversal when we hit every edge exactly once. Here, not so. So, for example, here in this one, I don't have a Hamiltonian path. There's no way. Now, we do want to think about the criteria that the graph should meet in order for there to be a Hamiltonian cycle in it, in order for the graph to be Hamiltonian. It turns out there are no useful, necessary, and sufficient conditions, although many sufficient conditions exist, and we'll talk about them a little later today, about sufficient conditions for a graph to be Hamiltonian. But anyway, okay, so this is not Hamiltonian. Let's see more of this. We need. Okay, can we argue why this graph is this graph Hamiltonian? So help me argue this. I think we're beginning kind of like relaxed here. We don't have like. Let's be very precise. Let's prove why there is no Hamiltonian cycle here. Let's argue this convincingly. So help me out. So this is called a bow tie sometimes, for obvious reasons, a bow tie graph.
Because no matter where you start, you will have to pass from the vertex C at least twice in order to go to the other way, if I can say it, to the other two vertices on the other side. And even if you start from C, then there isn't any way to go to the other side. If you go to D and
okay,
E,
so I get it. You can make that argument by cases. Can we argue it a little bit? So can I argue this? And the reason I want to argue it differently is because I want to draw people's attention to some other attribute of this graph. And what I'd like to draw people's attention to is the following. Consider a vertex that has degree 2. Like here you have 4 such vertices. A, B, D, and E. Each one of those guys, everyone other than C has degree 2. Now, what must be true about a vertex of degree 2? So if I had a Hamiltonian path in this graph, if this graph were Hamiltonian, that is, if I were to have a Hamiltonian cycle in this graph, if this graph is Hamiltonian, then the 2 edges that are incident to a vertex of degree 2 must be used up. Both of those edges must be used up. Do people agree with this? Otherwise, I just simply wouldn't pass through that vertex, right? So both of those edges must be used up. So now, suppose there is a Hamiltonian path here. So please follow this argument and tell me what you think. Suppose there is a Hamiltonian start. Suppose there is a Hamiltonian path. Then take a vertex of degree 2A. Both of the edges incident to it have to be used up. This means this edge has to be used up, right? The AC edge. There's no other way. Similarly, for B, because it has degree 2 and it's on the Hamiltonian cycle, both of its edges are used up. And therefore, this edge BC has to be on that Hamiltonian cycle. There's no other way. There's no other way for me to have a Hamiltonian cycle and not use the edge BC. Similarly, because vertex D has degree 2, both of the edges incident to D must be used up, meaning that CD edge is being used up. In a similar way, E has degree 2, therefore this edge CE is being used up. Otherwise, I wouldn't be passing through E. Now, what do we have as a result of this? We have that all 4 edges that are incident to C must be used up. And that automatically means that C was passed through more than once, exactly twice, in fact. So any traversal of the graph will have to pass through C twice, right? And any traversal of the graph that passes through vertices A, B, D, and E will have to pass through C twice. That is what we've proven, right? And then because every Hamiltonian path must include the vertices A, B, D, and E, and cannot pass through any vertex more than twice, and we'll see that there is no such Hamiltonian path, because anything that passes through A, B, D, and E will pass through C twice. Does that make sense? Okay, so that's this, where the bow tie is not Hamiltonian. Now again, so there are no useful, necessary, and sufficient conditions for the existence of a Hamiltonian cycle. We've identified a few necessary conditions. What were they? Remind me. So what was the necessary condition? If a graph was Hamiltonian, if G is Hamiltonian, then no way it has a pendant vertex, for example. That would be as a necessary condition, right? Then no vertices of degree less than 2. You cannot have an isolated vertex of degree 0. You cannot have a vertex of degree 1. That's true. But that's not a super useful condition. Okay, so there are also other necessary conditions that are known, but nothing super useful. For example, if you're familiar with does anyone know what a cut vertex is? So we're not covering the connectivity in depth here in this class, but if you've heard, does anyone know? If not, that's fine. A cut vertex.
It's like a subset of the, it's like a subset graph that, like, if you remove it, the graph becomes disconnected.
Yes, exactly. So here you have a graph, some graph, a bunch of vertices are connected. And if there is a way, if you have a vertex, which you remove, and by the way, when you remove a vertex, you remove all the edges incident to it, right? That's what it means to remove a vertex, because otherwise, if you don't remove those edges, you're not left with a graph at all. You have some edge that's not attached to something, that's where it's not a graph structure. So you remove a vertex, you remove all the edges that are incident to that vertex. So if you find the vertex that when you remove it, so for example, okay, so like this has a graph on 7 vertices. If you remove this vertex here, then you're left with something like this, a disconnected graph. So this vertex here, the one that I removed, is called a cut vertex, because I removed it and the edges that were incident to it, and I split the graph into 2 disconnected components. That's called a cut vertex. Okay, so Hamiltonian graphs cannot have cut vertices, right? That's another criterion. But anyway, you have a few criteria, the necessary conditions. Okay, okay, but there are none of them super useful. There are a few conditions, sufficient conditions, and that's not what we have here. I'm looking at a different slide. So, okay, so I'll return to this slide in a second. So since we're talking about sufficient conditions, let's get there. There are a couple of theorems known of sufficient conditions. One is called Dirac's theorem, and the other is called Orr's theorem. And both of them have to do with the number of edges that a graph has. Like intuitively, if a graph has enough edges, has way too many edges, then you're more likely to find a Hamiltonian path in it, right? Because you have more edges in your traversals to hit every vertex you want. So K, the complete graph, for example, that has every possible edge that you can imagine, a simple graph of simple graphs, then that's Hamiltonian. So the more edges you have, the more likely you are to find a Hamiltonian cycle. So here's what, let's take Orr's theorem here. Dirac's theorem follows from Orr's theorem, and Orr's theorem is not difficult to prove, but we're not proving it. It's actually one of the exercises in your book. If you're interested, we can talk separately, but here's what Orr's theorem says. Take any graph and pick 2 vertices in that graph, distinct vertices, U and V. If the sum of the degrees of those 2 vertices is greater than the total number of vertices in the graph, then that graph will be Hamiltonian. It's a sufficient condition. So it's sufficient for a graph G to meet this condition for it to be Hamiltonian. That's what we mean by a sufficient condition, right? So if every pair of vertices is such that the sum of their degrees is greater than n, then the graph will be Hamiltonian. Now, can you help me figure out why this is a sufficient condition? We haven't proved it, but it is. So if you just simply believe it, it is true. It can be proven. But why is it not a necessary condition? That we can argue immediately. So what do we mean? So what is it that am I asking? First of all, let's parse what is it that I'm asking. So make sure that everybody's on the same page. What I'm saying here is that looking at Orr's theorem here, this condition is sufficient but not necessary. So what does it mean to say that this condition is not necessary? Help me out. So what is the converse? So just purely logically, even if you like forget for a second what these, just purely logically, the theorem says that, okay, so
They can be less. They can be the same number of vertices. Can you hear me?
Same number of vertices?
Yeah,
Same number of-
same numbers are different, like depending on what scenario you're looking at.
Okay, so let's construct sentences. Now let's do English sentences and look at its logic. So let's go with the English sentences. So yeah,
You
somebody.
just want 2.2 the converse.
Sorry, one more time.
So you just want that theorem 2.2 in the converse.
Yes, what is the
So-
converse of this theorem?
So for every pair of non-adjacent vertices, U and V and G, what was the consequence? So if G has a Hamiltonian cycle, then G is like a simple graph with n vertices, and so forth.
Not so forth. We have to construct a sentence so we can think about it, right? No so forth. If every time you yield to the temptation of leaving your thought at so forth, you're not carrying out any mathematical argument, right?
So if G is a Hamiltonian cycle, then G is a simple graph with n vertices, with n being greater than or equal to 3, such that the
Yes.
degree-
Okay.
Yeah.
Okay, you're correct. If okay, so here's what we want to. Here's what we want. Anybody else? So that's what's correct. But can anybody else say the same thing? Like maybe in a shorter sentence, leaving the details out. Somebody.
Basically, you're just saying that even if these conditions, I'm sorry, it can be a Hamiltonian cycle if these conditions are not met.
Yes, exactly. That's what I wanted. So that's a shorter way of saying. So I know that if I take, so let's speak about simple graphs G, right? So the graph is simple, so let's not work that the fact that it's a simple graph into let's complicate the logical structure of it by working this into it. So let's talk, where our domain of the discourse is all simple graphs G, okay? Connected simple graphs G. Let's make it that, okay? Of all connected simple, so now the statements P and Q will be about connected simple graphs G. What this theorem says that if I have P is the statement that says if I have two vertices, U and V, whose degrees sum up to more than n, then the graph is Hamiltonian, right? So this is like Hamiltonian. These are degrees U and V greater than n, which is n is just simply the number of vertices. So the theorem says, all of our mathematical theorems so far have been of the form P implies Q. If something happens, then Q is true. Okay, it's pretty much like 99% of the theorems you see. So I'm claiming that if the sum of the degrees of U and V are greater than n, then the graph is Hamiltonian. As you've just suggested, the converse of this simply is if the graph is Hamiltonian, then the sum of the degrees of any pair of vertices U and V in it is going to be greater than n. Is that true or not? So is it true? The question is it true that if Hamiltonian, then the sum of degrees of U and V, where U and V are distinct vertices, greater than n. And again, n is the total number of vertices in the graph. So is that true? Now you may suspect you may know the answer. I guess I'm asking why it's not true. You can suspect that if you were to see this on a quiz, somebody just asked you, is it a true or false question? You will say, no, it's not true. The converse isn't true, because you know that this is, somebody already stated this as a sufficient condition only and explicitly said that, probably implying that it's not a necessary condition. And you're right, it's not a necessary condition. So why is it not the case that in every Hamiltonian graph, it doesn't have to be that if I find two vertices whose sums of degree are greater, I can find two distinct vertices whose degree sums are greater than n, which n is the total number of vertices in the graph. Okay, why is that? Can somebody help me out? I guess I want a counterexample. Okay, it's not a great drawing. Okay, let's stick with that. Is this graph Hamiltonian?
Yes.
Okay. what's the sum of the degrees of any two vertices that are distant from one another?
4.
Yeah, if you take any two vertices that are distant from one another, is going to be their sum is going to be 4, because in a cycle, every graph has every vertex has degree 2. Is this greater than n? Well, what is n here?
And it's 6 here, so it's
Okay.
definitely less than.
Yeah, it's definitely so. Let me write it this way. It's not greater than 6, which is n. Okay, so this is the converse. This is an example where the converse of Orr's theorem does not hold. So you can have a Hamiltonian graph with few. So intuitively, what is it? It's like if you forget all the formulations, roughly what these sufficient conditions say, these theorems say, is that if a graph has enough edges in it, then you'll find a Hamiltonian cycle in it. So enough edges in this case, the degrees of u and v when you have it. So the degree gives you some idea about the number of edges in the graph, because the degree counts the number of edges incident to a vertex. So if you have enough of those, it says, like in particular, if you have this condition hold, then you'll find a Hamiltonian cycle. The converse isn't true. You can have a perfectly good Hamiltonian graph with very few edges in it. Cn has the number of edges, that's just n edges, right? All right, so these are sufficient conditions. Now let's see, we don't want to, okay, so coming back to this, there are a few conditions that must be met. We already talked about a few of them. So you can't have a vertex of degree 0 or 1. We already talked that that is impossible in a Hamiltonian graph. Let me point out a couple. If you have a vertex and two edges incident to that vertex, then in any Hamiltonian cycle, both of those, okay, if you have, again, we already mentioned this, if you have a vertex of degree 2, both of the edges incident to it must be a part of a Hamiltonian cycle. That's that. If you have more vertices adjacent to it, like maybe you have others, like this, maybe that's a vertex, has degree, like, I don't know, 1,000,000 in a graph. Although that's such graphs. Okay, so you have a vertex of a large degree. Then on any Hamiltonian cycle, only 2 of those edges must be used up, right? You cannot use up more than 2 of them. So once you construct a Hamiltonian cycle, which by definition must include that vertex as every other vertex in the graph, and you find the 2 edges that are a part of that Hamiltonian cycle, you can eliminate every other edge incident to that vertex from consideration. You just pick the 2 that are a part of the cycle. Nothing else can be a part of the cycle. What else? Okay, so another thing is that the Hamiltonian cycle itself cannot be a part of any other larger cycle in the graph. Okay, it's inside, this is condition number 5. So let's look at the examples. Let's look at this one. So the claim I'm trying to make here with this example, that there is no, this graph is not Hamiltonian. There is no Hamiltonian cycle here. Sometimes it's easy to see this, sometimes it's difficult to, in general, it's difficult to determine whether a graph is Hamiltonian, but in some examples, you can see immediately. So these are the conditions to start checking for, right? So here, let's look at this one. Notice that M and K here have degree 2, right? This means that a Hamiltonian cycle, which must include those 2 vertices, will use up these 2 edges incident to M. Are people agreeing? And it will use up those 2 edges that are incident to K. So these edges here, this cycle will be completely used up. Every edge in this cycle then will be used up. What this means is that there is no Hamiltonian cycle, because our criterion is that this cycle here that we've shown has to be a part of the Hamiltonian cycle. It cannot be a part of a larger cycle. So you'll say, what? Okay, so I'm including these vertices here. So what about the others? How am I ever going to have any hope of including in my Hamiltonian cycle any of these vertices like C and H and so on, if I've already used up this cycle, right? So there's no way. Okay, so if I used up both of these edges, I'm not using, for example, LG edge, and therefore there's no way for me to have this vertex G as part of a Hamiltonian cycle. Yes, was there a remark? Or
Yes. So is that
Yeah.
to say that there's a unique for every graph, provided that it does have a Hamiltonian cycle? There's just one and only one cycle.
No, a graph can have several Hamiltonian cycles. This argument that we just gave does not imply that if a Hamiltonian cycle exists, it's unique. Is that what you were asking?
Yes.
Yeah, so it's not. You can have a graph. I think isn't this. So for example, this one, you can find it even in Q3, several Hamiltonian cycles, but I think we gave an example here. This graph, okay, there's one obvious Hamiltonian cycle around here, right? Around the edges, around the clock.
Yes.
And there's also another one. So there was another A, D, C, F, B, E, right? Or how did I go like this? Oh, this one starts at A. Anyway, you'll check. So A, D, C, F, E, B, and A. Okay, so started at A, and then so this is also a Hamiltonian cycle. You can have one that starts from symmetry considerations. Can you do this? Can you start at D? But anyway, that was the one that I just traced was another Hamiltonian cycle.
So you were saying that it just doesn't contain another Hamiltonian.
Yeah, it doesn't contain another smaller.
Okay.
Yes.
Thank you.
Yeah. So yeah. So it's good to have like these criteria like listed somewhere just to tell if so this one is immediately not Hamiltonian. Now it can get quite hairy, like determining if a graph is Hamiltonian. So for example, I have an exercise here at the end that's optional. Like this guy is known as Peterson's graph. It's a little bit more, it's not Hamiltonian, but it's a little bit more like hairy to argue that this is not a Hamiltonian graph. And it was much simpler to argue with this one, which is probably a little more complicated looking, maybe not so, but it's easy to argue that this is not Hamiltonian. Let's do one more before we leave. I can argue this quickly and then I think we can end. Although what I wanted to do today is I wanted to do some examples from extra practice, like one of these guys, but I'll do that next time. Okay, so here's, or you'll do it at the recitations, all those practice examples, but I'll try to do it in a couple in class as well. All right, so here's a graph. This is not a Hamiltonian graph. Okay, so now I'm looking back at my list of criteria here, the conditions that any Hamiltonian graphs must satisfy. Okay, so these are, okay, so these are the conditions. So let's look at, okay, so I'll tell you what the conditions are so that I'm flip back and forth. So let's just look at this example. Now, look at vertex number 2, vertex 2. Vertex 2 has a degree greater than 2. But any Hamiltonian cycle, if a Hamiltonian cycle exists, it uses up only 2 of the edges of 2, right? Out of 4, it uses up 2 edges so that it doesn't pass 2 more than once. So it just uses up 2 of those edges. The question is, which 2? Well, I don't know. So let's check every possibility. How many ways of choosing 2 edges out of 4 do I have? Well, it's 4 choose 2, otherwise known as 6. And here are all the 6 possibilities of the 2 ways of choosing of ways of choosing 2 edges out of 4. This edge and this edge, that's one possibility, these 2 edges. Here's another possibility, here's another possibility, like this edge, and so on. So you have all these possibilities here listed, 6 possibilities. So let's check each one of these 6 possibilities. Fortunately, you don't have to repeat the same argument 6 times because once you see the argument for one of them, the others are identical. So suppose, just for the sake of concreteness, that the Hamiltonian path that exists uses up these 2 edges. According to the criteria we have on one of the previous pages, I'm eliminating from consideration the other 2 edges. And therefore, I'm left with a graph that looks like this. It has 2 pendant vertices. Can it ever be a Hamiltonian cycle? Can this be a Hamiltonian cycle? No way. So what do I conclude? It means that I couldn't have eliminated these 2 edges. So that means that if a Hamiltonian cycle exists, these 2 edges are not part of it. This pair of edges is not part of that cycle. So one of the pairs of these 6 which emanate from 2, one of those pairs has to be it. So it turns out that no matter which of these pairs you try, you end up with a graph that has these pendant vertices, 2 of them. So there's no way for you to find a Hamiltonian cycle. So the conclusion is that this graph is not Hamiltonian. And we determined this just by looking at the necessary criteria that we have in one of the previous pages. All right, does that make sense to people? Right. Okay, so here's we should end here. Now in extra practice, so next time we'll talk about shortest paths. We'll talk about cost matrices representing weighted graphs. So a weighted graph is simply a graph in which edges have numbers assigned to them. The numbers can mean, well, the numbers depends what the context is in which the graph is used. It could mean cost, it could mean a distance between 2 points, and so on and so forth. We'll talk about that later. And we'll talk about Dijkstra's algorithm, and we also want to do some of these extra practice problems. Okay, so but that's for next time. All right, so let's end here. Any questions? So we're done with section 10.5.